Hi, this is the first in what I hope will become a series of videos in which I'll try to solve a problem, a math problem, without knowing the answer beforehand or the proof beforehand. Um, this is not my idea, and it's an idea I got from seeing a couple of recent videos of Tim Gowers, in which he tries to prove that Pascal's determinant is one, and over the span of 3 videos, he spends a couple hours and he ends up learning a lot about the problem. And you get to see all of his mistakes and the dead ends that he goes down. And I just thought it was pretty refreshing. As an undergrad, um, we're told sort of math is about making mistakes and stumbling and being confused all the time and getting stuck. But then you don't actually get to see that, and you only know of yourself getting stuck. You don't get to see your profs getting stuck, for example. They always come to class fully prepared to tell you the nice, neat solution. But behind every 2 or 3 line proof, um, someone spent hours and hours getting stuck and making lots of mistakes. So the format of this, I guess, will sort of be, I'll try not to use any other resources. So um, we're just gonna sit here with this is not paper, but as much as possible, it's like a pencil and paper, and I'll just try to prove something without necessarily knowing how that would look like beforehand. Okay, so that should be enough for an introduction. So what are we gonna prove today, or try to prove today? This is actually, I'm cheating a bit because this is something that I'm sort of familiar with. I almost a year ago stumbled across this identity, and it was really mysterious to me. And I thought about it a bit, but then I gave up. And at this point, I can't even really remember what the identity even was. But I remember finding that this specific sort of sequence of numbers that I plugged into something called the OEIS. So this is the OEIS. This is online encyclopedia of integer sequences. It's you can Google it, and I plugged this sequence in, and it told me that this sequence of numbers I found is actually the same as something else, another count of another thing. And that was really mysterious to me, and I thought about it for what must have been a couple hours, but then I don't really remember what I did, or and I just shelved it and didn't think about it too much. But I do remember what that sort of the 2 objects were, and today we're going to try to find the bijection. Okay, so on the one hand, this is what I was actually counting. I wanted to know how many binary trees. So a binary tree is a tree in which every node can have up to 2 kids. In fact, it kind of has like 2 slots for kids. So every node looks like that. It could have a kid on the left, or it could have a kid on the right. So, or a child. So a node can look like that, or it can just look like the left side, or it can look like the right side, or it can be a leaf with no children at all. Okay, and I was trying to count how the number of binary trees that look kind of like a big long noodle, like this. So this would be one. This is another one. So it goes right, and left, and right. I also allow this to happen. So the root could have 2 kids, but everybody else has just one. That also kind of looks like a big long noodle. And I want to know how many ways can this happen if the tree has n nodes. Okay, so that's where we're at so far. And the first thing is, well, let's try a few small examples. So when n equals 1, okay, there's only 1, and we'll say that's a spaghetti, or it's a noodle. It has, there's no branches to it. Like, what we don't allow is this to happen, where that's no longer a noodle. It's something with another little leg sticking out. So we don't allow that, but this doesn't have that. So we'll say that's allowed. And so there's 1 equals 1. There's 1 of them. Okay. Now when n equals 2, how many are there? We have the one on the left and the one on the right. And those are all the trees with n equals 2, so there's 2 of them. Okay, n equals 3. Now, how many trees are there? Let's draw all the trees with n equals 3. There's this one, there's this one, there's this one, and this one, and this one. I think there are only 5. And in fact, all of them are fine. So we have 5 here. Okay, n equals 4. Let's draw. So the thing about binary trees is there's a count for them. The number of binary trees is the Catalan number. Catalan numbers can be defined in lots of different ways. I hope I don't mess up their definition. I believe that the Catalan number, the nth Catalan number, should be 1 over n plus 1, 2n, choose n. Okay, and so 1, let's see if that actually works. So when n equals, let's say n equals 3. So 1 over 4, n equals 3, so 6, choose 3. Is that actually right? What's 6 to choose 3? I'm going to draw Pascal's triangle because I can't remember 6 to choose 3. 1, 2, 1, 3, 3, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. That's still 5, and then 1, 6, 15, 20, 15, 6, 1. Okay, so 6 choose 3 is the middle of this row. So that's 20. So we get 1 over 4 times 20, and that's equal to 5, which is how many trees we have. So these are all the binary trees. So the next one should be, well, the next one should be 1 over 5 times 8 choose 4. Now, how far do you have to go down to get 8 choose 4? 6 plus 15 is 21. This is 35, 35, 21. And then it'll be the middle of this, so it's 70, I believe. So it's 70 over 5, which is 14. So it should be 14. Is that actually right? Is 14 a Catalan number? Okay, well, it starts to get really hairy, right? So should we try to draw all of them? One, so we can go left, and then we have all these possible trees. Sorry. The first one goes left, and then we have all the possible trees of 3. So there should be 5 of these, right? The first one goes left, and then these 2. The first one goes left, and then those 2. Now the same thing, but we go right first. Right, and then we have this guy. Right, and then we have left, right, 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 left, right, left, left, right, and then right, right. These are 4 nodes. Now we're missing some more because we can have 2 children. So if we have 2 kids, that's already 3 nodes. We can only put 1 more. And how many ways are there doing that? There are 4 ways. So there's this one, there's this one, there's this one, and there's this one, and that's 14, I believe. So there's 10 up here, 4 down there. That's all 14. But that's not what we're actually counting. We're counting how many look like these noodles. So which ones are they? We have, let's pick a nicer color. This one, 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 and all of these guys. So it's all except 2. Okay. So that should be 10. Okay, so we have 1, 2, 5, 10, and we're not going to do the one for n equals 5 because that's going to take a really long time. But I think last year I seem to remember just drawing a bunch, so I probably went up to like n equals 5 and equals 6. Okay, I needed to do that because to get it into the OEIS, if you just put 1, 2, 5, 10 in there, I'm pretty sure it'll get confused and think there could be other possibilities of sequences that also have these starting terms. So I'm pretty sure I got more. But with this, okay, so let's try to find a formula for this. I don't remember the formula. I think I have a vague recollection of what it is. So yeah, once again, that's kind of cheating a bit. The whole point of this is to sort of discover it on the fly. But okay, so why don't I copy these numbers? And we'll try to get a formula that works. Okay. So how many ways are there? Okay. There's kind of two different types of noodles, right? There are the ones that start with one kid and then just have one kid all the way down. And there are the ones that have one kid and then, or I mean, the one on the right, same thing. And then there's the ones that have two, and now you have to, once you have two kids, you these both have to be one and just one all the way down. Okay, so if we have just one, if we just have one child, or sorry, let's say we have n nodes, and we'll try to count all these trees with n nodes. Let's do the one first. So we'll do the case where the root has just one child first. How many ways can the root have one child? It can be left or right. So there's two ways of having that, and then each one after that also has two ways. Two, yeah, they all have two ways going down. And there's so this would have 5 nodes, but the last guy doesn't have a child. So there'd be 2 to the n minus 1 ways. Is that right? So each, that makes sense. So each edge, we can think about it in terms of edges. A tree with n nodes has n minus 1 edges. And yes, and there's n minus 1. Each edge can either fall to the left or fall to the right. So there's 2 to the n minus 1. Trees on n nodes that are noodles that have one child at the beginning. Okay, and then now that's one of the cases. The other case is when you already have 2 kids at the top. Now that's almost the same, except that there's way less edges. We use 2 of these edges at the top, and they have to be there. Also, this is assuming that n is greater than or equal to 3, because you can't even have the 2 kids at the top when n equals 2. So what is this? Well, there are n minus 1 edges. There's always n minus 1 edges. So I think it's 2 to the n minus 3, right? Because there's going to be n minus 3 edges that can fall here. And they can fall either left or right. So there's 2 possibilities in each case. And so there's 2 to the n minus 3 ways of that happening. I'm convincing myself. I'm not so sure if this is actually the right answer. 2, so it's 2 to the n minus 1 plus 2 to the n minus 3. Okay, so that's 2 to the, that's 2 to the 2, so that's 4, times 2 to the n minus, what am I doing here? 4 times 2 to the n minus 3 plus 2 to the n minus 3. So that's Is that right? So it's 5 times 2 to the n minus 3. That seems odd, and that's definitely not. I've never seen this before, so once again, cheating, but it seems odd anyway. We can check whether it's odd or not because, or correct or not, because we can just plug stuff in. So when n equals 1, this is not going to be right. I made a mistake. 2 to the n minus, okay, again, we're assuming that n is greater than or equal to 3, so it doesn't even work for n equals 1. For n equals 2, that's correct. We have see, but that would say that, so it's correct here, and it's correct here, but it would say that when n equals 5, you have 2 to the 3 times 5, and that's 40. Is the next one 40? N equals 5, 40. I don't actually know, and I'm not sure I want to draw a bunch of trees to find out. I know a way we could check whether this is right or wrong. I believe that the next Catalan number for n equals 5 should be 42. And there's an easy way to check that. We'll just do this again. So 21 plus 35 is 56, 56. And now we add these two together. So we're getting to the limit of my math here, 126, 126. And twice 126 is 252. Okay. So that's 252 should be, this is the 10th row, I think. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so it should be 10 choose 5. So Catalan number of 5 is 1 over 6 times 10 choose 5, which is 252 over 6. What's that? It's 442. That's correct. So Catalan number of 5 is 42. So there are 42 trees, total binary trees on n equals 5. And so if this is right, then there can't be there can't be 3 binary trees that aren't noodles. But I'm pretty sure that's false because let's draw 3 binary trees on 5 nodes that aren't noodles. There's this one. Hang on. 1. There's 2. Oh my god, I'm not even. There's lots. So 1. That's 1. 1, 2, 3, 4, 5, and you could literally just do this. This one, that's 3 already. So 40 is not the right number there. So where did we make a mistake? So I believe, yeah, 2 to the n minus 1 seems right here. It's 2 to the n minus 1 ways of doing that. 2 to the n minus 3 seems right over here as well. 40 is definitely not correct here. Oof. N is greater than or equal to 3. There are 1, 2, 3, just n minus 3 edges, and then go every which way. So there should be 2 to the n minus 3. Did I just mess up in the computation here? 2 to the n minus 1. That's when there's one child of the root. 2n minus 3 is when there are two children of the root. Then we split this up into 4 times 2n minus 3 plus 2n minus 3. So that should be 5 times 2n minus 3. Oh, 3, not 2. Why did I write 2? Is that it? But that's not going to help because it'll just make it even bigger. Oh, wait. Oh, no, it'll make it smaller. Okay. 2n minus 3. So n equals. So that would say there's 20 here. That could make sense. 20. That still doesn't seem right. To the n minus 1 here, to the n minus 3 here. Okay. Are we missing some cases? To the n minus 1, 2 to the n minus 3. 5 times 2 n minus 3. Definitely seems off. Okay, I'm not sure what's going on here, but this is not. Should we draw all the trees? I don't really want to draw all the trees. I don't think that's the way to go. We got to find the formula. So, 1, 2, 3, 4. 1, 2, 3. Oh. 2. I'm not sure if it's. See, it definitely doesn't work because if we look, yes, this is wrong because okay. So what has happened? That's really weird. I think it's glitching. Okay, so the reason it doesn't work is because when you add a new node or when you add a new edge, we're thinking about, I'm looking at this picture. Okay, I know why I'm wrong. I'm looking at this picture and I'm saying that there are 2 to the n minus 3 ways of adding a new, there's 2 ways of adding the first edge, and then there's 2 ways of adding the second edge all the way down, and there's n minus 3 of them. And that reasoning would lead to there being 2 to the n minus 3 ways, right? That's not actually true, because if, say, I want to add a new edge here, I can do it here, I can do it here, I can do it here, or here. So it would actually be 4 to the n minus 3, I believe. 4 to the n minus 3. Does that make sense? Let's see what that gives us. Right, because then it continues, because you have like that. Say we choose one. And now there are still 4 ways I could put a new edge. There, 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 or there. Okay, so 2 to the n minus 1 plus 4 to the n minus 3. This is 2 to the n minus 1 plus 2 to the 2n minus 6. I think. And now we get something kind of 2n minus 6 minus n minus 1 is n minus 5. So 2 to the n minus 5 times 2 to the n minus 1 to the n minus 1. So we add them, we get 1 plus 2n minus 5 to n minus 1. Which, once again, doesn't seem like something I've ever seen before, and doesn't seem like it's right. Let's try. What would that give for 5? So it'd be 1 plus 2 to the 1. N minus 5 is 0. So times 2 to the 4. So it'd be 16 times 2 is 32. Is that right? Okay, anyway, so we got a little far enough. I think at this point, this is where I'd be going into the OEIS and typing stuff in. And what I actually found is that this is apparently the same sequence as the number of ones in all compositions of n plus 1. So a composition of a number n is all the ways of writing n as a sum of positive integers. So for example, there's one composition of 1. It's just that. There's how many compositions of 2 are there? There's 1 plus 1, and there's 2. Yeah, that's 2. And so 3, there's 1 plus 1 plus 1. There's 2. There's 1 plus 2. There's 2 plus 1. So we, even though that's it's the same thing like commutativity, we do count them as different if they have different ordering. And then there's just 3. Okay. 4, let's do one more. 1 plus 1 plus 1 plus 1. 1 plus 3, 3 plus 1. Now what else? 2 plus 2. I'm not doing this in any principled way. Was it 1 plus 2 plus 1, 2 plus 1 plus 1, 1 plus 1 plus 2, and 4. Okay? And there are 2 to the n minus 1 ways of doing that. And the way to see that is a composition is sort of the ways of divvying up your number. We'll just, with balls, we can just draw, say we have 6 balls, okay? And we want to divvy it up into compositions. So if we just look at it like that, that's 6, right? Let's say we do that. Well, we like put a little divider there. Now we have 2 plus 4. Okay, so the number of compositions is the number of ways of either putting a bar here or not putting a bar here. So there are 5 spots we can put a bar. Oops, 5 spots, 3, 4, 5, and each one could either be there or not there. So there are 2 to the 5 ways, and that's 32. So there are 32 compositions of 6. Okay, and so this is saying that when I plugged it into OEIS, I found that the number of these Noodle trees is the same as the number of ones in the compositions of n plus 1. So okay, it said number of ones in all compositions of n plus 1. That's actually what it says in the OEIS. But I'm pretty sure that their sequence is shifted down a bit. So like n equals 0 would be that, and that's n equals 1. So it's really the number of ones in all compositions of n. And that seems to be correct, because if we do a little highlighting here, this has 1. There's 2 here. There should be 5 here, if that's correct. 5 there, and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. There seems to be 12. So is that a problem? Okay, we went, that's a problem. This is 12. And what happened is I did 14 minus 2 and I got 10. And so that's embarrassing. N equals 4 should be 12. Right, there, just check again. There are 14 trees here total, and there are 2 that are not noodles. And so that's 12. So we have 12 here. And why don't we now check what it is for 5? We can check if it's actually 32, which is what this formula would say. Actually, did we check the formula for n equals 4? Let's check it. 1 plus 2 to the n minus 5. See, that's the problem. There's an n minus 5 here, and that's not supposed to work. Oh, no, it's okay. So we'll say 1 plus a half times 2 to the n minus 1. So 2 to the n minus 1 would be 8. So 2 to the 8. So sorry, 2 to the 3, which is 8. So it's 2 to the 3. So 8 times 1 plus 4, that's 12. Okay, so it actually does seem to work. And yeah, it would say that it's 32 for n equals 5. So let's write out the compositions of n equals 5 and see if it's 32. Okay, so we have 1. There's going to be a lot of compositions. There's going to be 16 compositions, and we're hopefully going to find 32 ones. So 1 plus 1 plus 1 plus 1 plus 1. And then we have, I want to organize this in a nice way, but I'm not really sure how I'll do it. 1 plus 4. Let's just go 4 plus 1. We'll do all the 2 first. We should really be doing it this way. Let's start. Let's go backwards. So 5, 1 plus 4, 4 plus 1, 2 plus 3, 3 plus 2. And then now we need to have 3 of them. So a way of having 3 is 1 plus 1 plus 3. We can have 1 plus 3 plus 1 and 3 plus 1 plus 1. Another way of using 3 digits is 2 plus 2 plus 1. So 2 plus 2 plus 1. 2 plus 1 plus 2 and 1 plus 2 plus 2. So how many do we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We need 4 more. Let's try with 4 numbers. So 1 plus 1 plus 1 plus 2. And then all the other places will put a 2 plus 1 plus 2 plus 1 plus 2 plus 1 plus 1 and 2 plus 1 plus 1 plus 1. And that should be all 16 of them. Let's check again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't really trust myself with doing things correctly. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So that's not 32, which is 18, making sure I didn't miss one. So it's 28. 28, not 32. So this should be 28. So what's the problem? Is there a restriction on where these? So I'm pretty sure this is correct. If there's only one child at the top, there are 2 to the n minus 1 ways of putting those. Yeah, because it can only attach to the bottom node. So like I drew here, you can only attach here. If you attach anywhere else, so what am I trying to say? If you attach here, you're going to create a non-noodle. You can go there or there. That's bad. If you attach at the top, well, it's still a noodle tree, but it will get it will fall into this other case, which we're trying to count. So this whole thing is splitting it to the n minus 1, and then something else seems to be correct. I just can't get the else to be correct. So why don't we erase everything and try again. So we know that's wrong. So we just, let's erase it. So we should get 28. That's the number to get. This is a lot easier than drawing all the trees. So I should say, by the way, that the goal when I sat down to do this video is to find a bijection between these green dots and the trees. Now, I don't know if that's a lofty goal, because what in the world do trees have to do with these parts that equal 1 in compositions of n? I have no idea. But in combinatorics, the nicest proofs are always the proofs where you count something, or 2 different counts, either the same number or you count the same thing in 2 different ways, and that gives you an identity. So that would be really nice to have. But it seems like I'm not even going to be able to prove that the count is correct in this video. So maybe let's try to make that the goal for the remainder of this video, is to find out what the formula is and show that the formula counts these trees for 1, and maybe show that the formula actually counts the number of parts in all compositions of n plus 1. Yeah, bijection would be probably too hard at the moment. We can't even get the formula right. Okay, so we're kind of back to the drawing board. What have we done? We've figured out that n equals 5 should be 28 and not 32. So let's cross that out. So how do we do that? Well, another way we could do this is to sum over the possible I don't know. What I was thinking is we could sum over the possible splitting. Like, there's going to be n minus 3 edges left. I guess. Ooh, sorry. There are going to be n minus 3 edges. Also n minus 3 nodes, depending on how you think about it. And they need to go into this tree. Some of them are going to go on the left, and some of them are going to go on the right. And is it different depending on how many are on the left? I guess, because if all of them go on the left, say n minus 3 of them go all on the left, there are 2 to the n minus 3 ways of that happening. Okay, but then if all of them go on the right, there's 2 to the n minus 3 ways. I just think that it's a bit stupid to sum over all of them, because if, say, we put it's n minus 3, right? Let's say we put some of them on here. Say half of them go here, half of them go here. N minus 3 is, let's say n minus 3 is even, so we can split that exactly in half, well, then what happens is we have the number of ways to do it on this side times the number of ways to do it on that side, which ends up being 2 to the n minus 3 anyway. Or 4 to the n minus 3. Just turn off my notifications. Let's do that right now. I can probably just turn off my Wi-Fi. That's what I'm going to do. Okay. Now, so it really does look like 4 to the n minus 3 is the correct count here. That we know that doesn't work. There's one way of this happening. Now there's another. We're going to add n minus 3 nodes to this tree. Did we just make a computation error? 4 to the n minus 3. Okay, let's try not to simplify, which I did last time, and let's just look at this. So if n equals 5, we have 2 to the 4 plus 4 to the n minus 3 would be 4 to the 2, which is 16 plus 16 is 32. Yeah, no, so I didn't simplify wrong. It says 32, but there are only 28. So there has to be some kind of overcounting going on here. We're counting 4 of the trees too many times in this way. Yeah, we're double counting 4 of the trees. Which 4 are they? I got it. Okay. This is what's wrong. If we look at this, I'm gonna put a node. I'm gonna put a node here, and then I'm gonna put a node. Yes, I'm drawing it wrong. I'm gonna put a node here, and then I'm gonna put a node here. That's the same thing as if I first put a node here, and then put a node here. But we counted that twice. We're overcounting the ways to do something, I think, is the problem. Okay, so we're gonna try to let's tailor our approach to just n equals 5. So if there's 16 here, there should only be 12 ways. Okay, what are the 12 ways? If we put a node here, then there are 1, 2, 3, 4 ways of putting the last node. That would be 5, so there's 4 of those. Oh, the counting is really odd. Let's just continue. There should be 12, right? So now we're going to do something completely different and put this one here. And now there are still 4. So we erase that one, and there are still 4, right? These 4. That's 4. Now we have to be careful with the last 2, or I mean, if we put this second last node there, we can't take this one or this one because we already counted those last time. But these 2 are both fair game, so there's 2 more, and then there are 2 more here. So this, 2 more here. Okay, so 2. So it's 4 plus 4 is 4, that's 12, and 16 plus 12 is 28. So that's correct for n equals 5. Is there a way of making that a rule, though? You know what? I think let's just do this. The summing might be the correct way to go. Because there are n minus 3 left. And so some of them have to go on the left, some of them have to go on the right. If we fix a certain k of them go on the left, so n minus 3 minus k of them go on the right. 2 to the k, no, that's not going to work. What is the way of... Try back where we started. Four ways. Now there are 3. No. I suppose some of you are, if you're watching this video, are probably like tearing your hair out if you've already seen it or seeing what's wrong. At least seeing what's wrong, maybe even seeing the solution. I'm probably just going insane right now. But I'm not seeing it. Which is quite frustrating because I have actually done this before, but it was, like I said, a year ago. So I don't remember the formula or how I did it. There may have been a way to do it recursively. Say that we know how many trees, I keep calling them noodle trees, how many noodle trees there are on n equals 4. Does that in any way tell us how many noodle trees there are on n equals 5? Yes, I guess. Because look, if for every one of these trees, we can continue to make it a noodle tree by adding left or right. Left or right, left or right, left or right, left or right. And they're all different. You're not going to get the same one twice, I believe, because the tops are different. So we can start by saying, well, the number of ways to do it will be, for n equals 5, is 2 times, let's call this, we'll call it Tn. So Tn, so T5, we can start with 2 times T4, so that's already 24. And then this is sort of saying that there are only 8 left. Not 8 left, there are 4 left. So what are the 4 trees that you can't make? 4 noodle trees you can't make in this way? Well, they've got to be the ones that, because look, you can even make ones that are like, oh. There are 1, 2. 1, 2. Oh no, that's gonna be lots of them. 2 of them, 2 of them, 2 of them, 2 of them. But then look, there's this, there's this. What's happening there? It doesn't seem pretty. One. We didn't count the ones with 1 separately. Then we kind of go back to what we did before, because if we want to count the ones with just like a single string from the top, that's 2 to the n minus 2, and we're timesing by 2, So that's 2 to the n minus 1. So that literally goes back to this way of counting it. And then now we need now we're trying to do the other case where we started with 2 on top, and now we're trying to find all the ways of putting another one here. And why was it bad to we just want to add one node here. Why is it bad? Huh, why doesn't it work? Okay. Oh, the reason is because adding a node here, for example, is the same as adding a node here. You get the same tree. So there are 2 ways of doing each one. This is a pretty complex counting problem. At least it seems so to me. I think there should be a way of summing. Let's go back to this. So if we add 1 here, oh, if you add 1 here, how many possibilities are there now? Adding the 5th one. There are 4. 4. Okay, now if we add 1 here, how many ways are there? There are still 4. Now we've gone and summed over the whole first side. And on the second side, we have 1, say we like this. Now there are only 2 ways. We don't count any of the ones on this side because we've already done them. We've counted them before. So there are only 2. Okay. Is that it? So we need to decide how many go on the left, then how many go on the right. Sorry, my brain is just going, like flipping back and forth. I don't, this sounds like it'd be hard to compute, so I don't really. I'm wondering if there's a way to do it recursively still. Each of these guys Something's going wrong. Okay. Well, let's change tack actually, and let's try to count how many ones there are in all compositions of n plus 1. It's the same number, so we're going to get a formula presumably that is it's the same. Maybe, and then we can try to go back and see why that's true for the trees. So once again, we're using sort of what we know or what we want to show. And yeah, okay. So what are the number of ones? Well, where do we start? Let's start with if there are a certain number of parts. Nope, why don't we start with if we start with a 1, this is a way of maybe doing it recursively. If we start with a 1, so we start with a 1, all the ones where we start with 1. I'm going to hold this here. Then those rows are all the compositions of n minus 1. There are 8 of them. Right? There's 4, 1 plus 3, 3 plus 1, 2 plus 2, then all the ways of 1 plus 1 plus 2, and 1 plus 1 plus 1 plus 1. And so the number in those rows should be, like, just counting for all those rows, it should be the previous number. So if we write all these, we're still going to call them Tn. Let's go this way. N, Tn, 1, 2, 3, 4, 5. What do we have? 1, 2, 5, 12, 28. 1, 2, 5, 12, 28. And so now we see here, if we just circle all these again, if it starts with a 1, then we have the number of ones in the previous iteration, so 12. So if you look, I can't point because I'll lose my circles, but if you look at the rows containing the red circles, there are 12 green ones, not counting those red circles. So if we just count those rows, so rows beginning with a 1, well, how many are there? There are, if we just count the green guys, there's t to the n minus 1, and we still need to add how many there even are. That's 2 to the n minus 2. Okay, 2 to the n minus, that would make sense, because how many compositions are there even of n minus 1? There are 2 to the n minus 2. That's what we showed with the stars. This is called a stars and bars argument, or dots and lines, another way of doing it. Okay, now we look at the ones, let's try to count the other ones. So the rows without a 1, so we can cross all these out. Now now what's the problem? Okay, this is a bit harder to count. I don't really see the pattern. We have 3 ones in one way, 2 ones in 2 ways, and 1 in 3 ways. Or sorry, and 1 in 1 way. Is that a 2 ones? No, hang on. What am I trying to say? There's 1 in 3 ways, 2 ones in 1 way, 3 ones in 1 way. That's not. Is it how many are there even? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. 8 of them. If we don't start with a 1, then those are ones in all compositions of, oh, huh. Okay, let's I really did this badly, because let's look at the ones that start with a 2. There should be 4 of them, right? Because that's 2 to the, so there are 4 of them. And these are all the compositions of 3. If we just look at, let's circle the rows instead. These are the 4 compositions of 3. But we know how many compositions, or how many ones are in the compositions of 3, because that's t to the n minus 2. And so if the pattern continues, we would have t to the n minus 1, n minus 3, sorry, and so on. So is that right? Does it seem like it's 2 to the n minus 2 plus the sum of I equals 1 to n tn? That might be it. let's test it out. So you sum all these up, you get 1, and then you do 2 to the n minus 2. That's a half. Okay, it doesn't work for 1. What about for 2? Yeah, that might just be because it doesn't. With 1, it's like the base case, perhaps. Okay, so so it'd be n minus 1 here. N minus 1. Let's try this. So 2. You sum all these. Oh, what am I trying to say? Yeah, okay, so you want to sum all these up. So 1 plus 2 to the n minus 2 is 1. So that gives you 1 plus 1 is 2. Okay, perfect. Now the next one, we have 1 plus 2, and then we add 2 to the n minus, 2 to the 3 minus 1, which is 2. That's 5. Okay, I think it's starting to work. So 1 plus 2 plus 5, and then we add 4. So that would be 9, 12. Okay, let's do one more. 1 plus 2 plus 5 plus 12. And then we want to add 8. And that gives us, this is what? It's 8, 20, 28. This seems to be a correct formula. It's not quite a formula yet because, well, we want to say that this is Ti. So the formula we have, so formula is T, so T1 equals 1, Tn equals 2 to the n minus 2 or 1, 2 to the n minus 2 plus sum I equals 1 to n minus 1 of Ti. Let's try to, okay, what are we doing? Now, is there a reason why this doesn't look anything like, or sorry, if we take this and let's just put it by the trees so that we can burn it into our retinas here. This is supposed to count these. Now, why is that? 2 to the n minus 2. So we have 2 to the n minus 1 here. Presumably, if there's another one of them, then we'd have 2 to the n minus 2. So 2 to the n minus 1 plus 2 to the n minus 1 is 2 to the n minus 2. So there should be another 2 to the n minus 1 here. And then here we will have a sum I equals 1 to n minus I equals 1 to n minus 1 Ti. Why is that? Oh wait, what am I saying? This is this is bigger. This is small. Sorry, this is smaller than that. So that's not actually right. I'm not seeing this recurrence. Sort of doesn't really seem to say anything to me right now regarding the trees. Why don't we solve the recurrence? That could be a way to go. We'll solve the recurrence now. This is a little bit. Once again, it's kind of scary because I haven't solved the recurrence for a very, very long time, or at least a few months. How do we do that? We want to find, is it substitution? We substitute into, yeah, this is no good. T, 2 to the n minus 2 plus, okay, let's just look at it. This is the naive way of looking at it. So T1 equals 1. T2, if we put, if we look there, it should say, it would be 1, 2n minus 2 is 1, plus T1, so that's 1. Okay. T3 will be let's write this out. 2 to the 0 plus 2 to the 0 plus 1. Okay. Now we have 2 to the 1 plus, and then I'm going to put this here, 2 to the 0 plus 1. That's T2 plus another 1. So T3, T4, sorry, will be 2 to the 2 plus, I mean, this whole thing. So 2 to the 1 plus 2 to the 0 plus 1 plus 1. That's 3 plus 2 to the 0 plus 1 plus 2 to plus 1. So how many times 2 to the 0 shows up twice? 2 to the 1 shows up once. Let's see. Okay, let's not scrap this. We could try summing. What am I? No good. 2 to the 2 plus 2 to the 1 plus 2 to the 0. Okay, all right, let's just do it one more time. So 2 to the 3 plus this whole thing. I'm just going to copy it. Copy, paste, and then plus 2 to the 1. So this is all one thing. Plus 2 to the 1 plus 2 to the 0 plus 1 plus 1 plus 2 to the 0 plus 1 plus 1. Now, how many times does 2 to the 0 show up? 2 to the 0 shows up 4 times. Okay, this might be a pattern. 2 to the 0 shows up 4 times. 2 to the 1 shows up twice. 2 to the 2 shows up once. 2 to the 2. Okay, so let's cross all those out. Or I don't think cross it out, but that's that. And now how many 1s are there? And there's always going to be that 1, 1, 2 to the 3. And then how many 1s are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 8. And are there 4 here? 1, 2, 3, 4. 1, 2, 1. And that's just 1. So that's what's happening. This is the 2 to the n minus 2. It's really interesting because we thought the 2 to the 3 here is an 8, but there are also 8 1s. So there's kind of 2 ways. It's almost like symmetrical because the number of 1s here is going to equal this guy. And at least I think so. 2 to the 1, and there's 2 1s here. 2 to the 2, and there's 4 1s there. That's kind of interesting. So plus 2 to the n minus 2. Sorry, 2 times 2 to the, 2 to the n minus 2. So 2 to the 3. Now what is this pattern? I want to stay on the same page, so let's just remove this. Something's got left behind. Let's move this up. So in general, we will have, so what were we doing? This is the number of 1s. This is the sort of the powers that we see inside after unraveling the recurrence. And this is the number on the side. So the number of 1s always equals 2 to the n minus 2. So why don't we add them together? So it's 2 to the n minus 1. And now, do the exponents add up to something? They do, because this is 2 to the 0 times 2 to the 2, so that's 2. This is 2 to the 1, that's 2. It's 2, so it's 2 to the n minus 3. Now, if this is actually correct, then I'm going to be really angry because we did this. We had this way, way, way back when, like an hour ago. So why did we think it was wrong? Two to the n minus 2 to the, I'm confused. 2 to the n minus 3 for 5. 2 to the, it's 2 to the 2 plus 2 to the 4. No, this is wrong. What have we done wrong here? 2 to the 3? No, 2 to the 2 plus 2 to the 4. That's 20. So that's what we got the first time, but it's not 20, it's 28. What am I saying? There are 3 of these. So we forgot a 3 here. So it's 3 times 2 minus 3. So that's 3 times 4, which is 12, plus 16, which is 28. Okay, that's correct. 3. And in general, it would be n, no, not n, n minus 2 times 2 to the n minus 3 plus 2 to the n minus 1. Does that simplify into something nicer? I think we got the formula correct now. So it's n minus 2 to the n minus 3 plus 2 to the n minus 2 to the n minus 1. There's 2. Why am I in red? So that's n minus 2. Let's. It's n times 2 to the n minus 3 minus 2 to the n minus 2 minus 1. No, that's not nice. Let's get it bigger. 2. I think it's n times 2 to the n minus 3. Is that right? Because there's 4. No, that's wrong. This is equal to n minus 2, 2 to the n minus 3, plus 4 times 2 to the n minus 3. So that's equal to n plus 2, 2 to the n minus 3. I think that's the formula. Okay, let's write out a whole bunch of them to see if that's right. So n plus 2, so n plus 2, 2 to the n minus 3. We know that it doesn't work for n equals 1, so let's just, we'll highlight it special. Actually, does it work for n equals 1? N plus 2 is 3. 2 to the n minus 3 is something that is a fraction. It's like a quarter. That's 3/4. It doesn't make sense. Okay. But for 2, n plus 2 is 4. 2 to the n minus 3 is a half. So it's 2. For 3, it's 5 times 1. That's correct. 4, it's 6 times 2. It's 12. 5, it's 7 times 4, 28. And so it's saying that 6 should be 8 times 8, 64. Okay, so I think that we've counted correctly, I think, the number of compositions in n. Now, what does that have to do with trees? I'm actually really annoyed that I can't figure this out, because this is actually where I started a year ago, and I was able to do it then. So okay. I'm gonna give it one more stab. I know the video is getting really long. I'm gonna give it another stab, and because I really would like to have this in the video. So now we know the formula. So it's n plus 2 to the n minus 3. The problem is it's such a nice formula that it's sort of like unclear where it would even come from. N plus 2 to the n minus 3. What are we counting n plus 2 of? That would have 2 to the n minus 3 possibilities. N plus 2. 2 to the n minus 3 is the number of possibilities of after. Did we settle on that being wrong? Maybe this is, if we show they have the same recurrence. So 2 to the n minus 2, that's the number of ways of putting some items on 2. What in the world does it have to do with? So it's saying that the formula or the recurrence is saying that the number of noodle trees with 5 nodes has something to do with this sum. If we look at all of these trees, all of them, each of those are counted once, and then you add another 2 to the n minus 2. But each of these trees should correspond to exactly 1 tree of 5. I'm not really sure what that tree would be. Okay. The video is actually getting really long, so I'm going to stop here. It's a bit of a cliffhanger, but I will get back to this and we'll pick up. And in the meantime, I'll try not to think about it too much because I want to capture all of that in here. But yeah, okay. So I'll stop here. Do let me know if you guys see anything. And otherwise, I will see you next time.